Thank you for
Sure.
being here.
Yeah, so just a little brief introduction. I'm a postdoc scholar at the Space Sciences Lab at UC Berkeley. And mostly there, I actually study Mars. Specifically, we're interested in using the MAVEN data set to understand the magnetic field of Mars and try and sort of back out from there to understand the former history of Mars and why it looks like what it looks like today. But what I wanted to talk to you about in this talk was actually some work that I was doing in my PhD thesis at Michigan. My advisors there were Shinja Jha and Michael Lamone, if you know them. And really where this has gone since my thesis is trying to develop interpretable, ergo usable machine learning for planetary science and space physics. And so really to get us started, I want to provide some definitions and some current trends, right? So I want to ground us a little bit in seeing where our field planetary science is in machine learning, and where we are in terms of interpretable machine learning, and I'll define what I mean by interpretable. Then we'll sort of move to an application, building off my thesis work, talking about machine learning for Saturn's mass transport. So what does plasma and mass moving around the system of Saturn look like? And finally, we'll go over something a little bit more forward-looking, trying to see where our field can go in incorporating these different types of methods into our work. So just sort of starting out, I want to have a shared definition of what is machine learning. And this is a pretty broad definition, but you can generally consider it to be computer algorithms that improve or learn through inclusion of data or observation of data. This means that machine learning methods tend to be highly flexible, and they're designed to adjust their parameters to the structure of the data, and they tend to be used as models that make predictions. These models tend to range in complexity. You can have models like linear regression all the way up to neural networks, which tend to be the more popular ones being discussed right now. And you can have applications ranging from, say, planetary surface recognition, image classification, to then trying to find patterns in your data. There's a lot of different uses of these machine learning methods, and I would say that the scientific community is still learning about these things, and we're still exploring about how these can become part of our toolbox. Recently, in my field, planetary space physics, applications have tended to focus on prediction. So for example, solar flare prediction is a very common topic that you see being discussed for machine learning. But machine learning methods in general can be used for really both prediction, right? So solar flare prediction, or for gaining greater understanding of your data, or inference and statistical learning. And that's really where I'm interested, and we'll circle back to that a little later in the talk. But as we move forward, I think it's important to consider where planetary science is compared to other fields. So this is a chart of all the publications mentioning machine learning across the 4 NASA divisions. These are just easy filters for the fields of space-interested science. And this is a fraction of how many publications address machine learning compared to the overall publications in these fields. And so over time, since about 1995, which is how far I extended this analysis, you can see that machine learning as a term has sort of picked up in publications literature. And I'll talk about this gap between planetary science, which is blue, and all the other NASA fields in a second. But just for comparison, the term modeling, which really includes different types of scientific modeling, this covers about 50% of publications in planetary compared to 2% for machine learning. So just to sort of provide some perspective. But as we were discussing actually before this talk, machine learning isn't a new concept, it's not a new method. And you can date NASA being interested in incorporating machine learning just about back to 1980 with this report chaired by Carl Sagan. So if these were the methods being discussed, really what is happening or circa 2005 onwards, that have resulted in this exponential increase in publications discussing machine learning. Okay. For comparison, to start to explain why machine learning publications are growing, we have a mission of the era that the Sagan report was coming out of, the Voyager missions. The data size, the data return of a mission like this, to our nearest estimation, is on the order of about 100 gigabytes. Whereas missions like the Mars Reconnaissance Orbiter, MRO, the data size being returned from missions like this is on the order of terabytes. MRO in particular is rather interesting because that mission alone has collected more data and returned more data than all interplanetary missions present and past. So we're really seeing for Planetary a great increase in the data sizes compared to missions closer to home. There's a mission called the MMS mission. This one alone is collecting on the order of 13 gigabytes of plasma relevant data per day. There's also missions like TESS, which is focused on exoplanets. This one is collecting 27 gigabytes of data per day. And then coming out of solar physics, Solar Dynamics Observatory has already collected at this point 20 million gigabytes. And where this is pushing, and why I think machine learning, one of the reasons why it's been increasing in our field, is that these data sizes are really pushing space physics and planetary science to consider automation not only as a useful thing, but as a necessary thing to engage in either these prediction or inference tasks that we're interested in. And so what this could look like, the TESS mission, for example, returns about 1 million light curves per month. If you're trying to analyze 1 million light curves per month for potential exoplanets, that's going to start to necessitate automated methods. And so this is what I mean by automation is necessary. The data sizes are just becoming overwhelmingly large for any types of traditional by hand or by eye methods. Now, where planetary science differs from other fields is actually that we tend to find prediction tasks for machine learning to be limited. So, for example, for machine learning for, say, space weather, you really care about how accurate a prediction model is for the sake of protecting Earth's assets from different space weather risks. For planetary science, there's rather limited appeal to predicting, say, the space weather at Saturn, because we don't live on Saturn. And so that's part of the reason why I credit this gap between planetary science and other fields. Another reason is that planetary science just has problematic data that can be difficult to deal with when using machine learning methods out of the box. So we tend to be interested in events that are rare. We tend to be interested in events that have a characteristic space and time variable running through them, or spatial temporal sampling. And in a lot of cases, we're dealing with the first ever observations of different systems, which creates a difficulty in knowing what to assume about the system. And so what's being shown here is just a selection of orbits from the Cassini mission, showing how many different places around Saturn in the middle that Cassini went, and how this by itself means that space and time create this rather challenging data set to automate. So what we're interested in here is how can we use machine learning to really advance our understanding of these complex systems, but do it in a way that answers fundamental scientific questions. And this is where interpretable machine learning comes in. This is also known as physics incorporated or model adjusted or theory guided machine learning. And I've provided some author works so that you can sort of see in different fields what this is being called. But really the primary goal of creating methods that are including physics and creating interpretable methods is so that you can use the machine learning systems that already exist but do it in a way that both asks and answers scientific questions. And in doing so, I'm going to say that you can deal with inherent data challenges in planetary data sets. And so one way I like to think about sort of where this fits in the grand scheme of scientific investigation is through this flowchart on the right. On the left side of this flowchart, you have something that our field in space physics and planetary space physics has been doing for quite a while. It's, for example, a model-bound system or something where you have a physics-based code that you're advancing forward in time or space and seeing what the outcome would be. Something like this is purely theory-based. On the other side, you'd have something where you're interested in, say, predicting solar flares, and you want to let the model vary because really what you're interested in is the most accurate prediction. You don't necessarily care what the model itself is doing underneath the hood. In the middle is what I like to call model-adjusted machine learning, where you're taking advantage of data science techniques or machine learning methods, but you're including what you know about the system, including physical understanding constraints. And this allows you to answer more scientifically driven questions about complex planetary systems. So I want to move to an example of what this actually looks like in practice. And we're going to move to using the Cassini-Huygens, there we go, the Cassini-Huygens data set to really see what interpretable machine learning might look like. So in this case, we're particularly interested in a type of event that occurs in the magnetosphere of Saturn. So this is a picture looking top down on the magnetosphere of Saturn. You can consider the bow shock and magnetopods as sort of the outer boundaries of the system we're interested in. And here is an illustration of the Cassini trajectory moving through this system. So one of the things the Cassini-Huygens mission did, one of the big findings, was that it discovered that a moon of Saturn, Enceladus, is outgassing a large amount of water and water-like material into the system. And this creates a very dense, neutral, and plasma environment around the planet. As a result of this dense system, of this dense material, you end up with these two distinct particle populations, one which is very dense, close to the planet, and one which is less dense, more energetic, further away from the planet. And somehow these two particle populations have to mix or interchange so that different quantities are conserved in the system. So this material needs to leave and this material actually needs to travel towards the system. How this works, if you're familiar with any types of fluid dynamic system, is that it's most similar to something called a Rayleigh-Taylor instability. And you can actually see the same type of physics happening if you drink coffee and you pour something really dense like cream into the coffee. You have a force pushing down, but you actually have something dense on top of something less dense. And so this is inherently unstable. And you end up having these two populations intermix. And so then you have a delicious drink at the end of the day. But at Saturn, the most close analogy is that this dense Enceladus material is the cream in the coffee, and the coffee is the less dense, highly energetic material. So moving on from something very schematic to what the raw data looks like, this is sort of a classic picture of the types of data you get off the Cassini mission. So we have 3 different sensors being represented here. And as the spacecraft moves along from left to right, it's collecting different information. And what we see is that there's sort of this nominal information or a nominal background that's in all these charts. But then you have these 4, there's a 4th one here, it's a little smaller. You have these 4 distinct transitions between something which is sort of the average background and a completely different plasma population. And so what this represents is that as the spacecraft moves along, it's passing over different types of interchange events, where these instabilities I was talking about and it has some correlating signatures about it, including high energy ions and magnetic field. And I'm being a little quick with the space physics part of it because of who I think is in the audience, but if you have more questions, you are welcome to ask them later. So where we were really interested in going with this is we wanted to know how all these different events in the Saturn system were distributed. We wanted to know what implications this had for how mass moves around Saturn, because that's a really important question for space physics, is how anything moves around a planet is really useful in understanding planetary evolution. And so our goals here were to identify, standardize our identifications, compare it over the entire Cassini mission. So that would be 13 years of data. And then work on determining more physics-based questions, including what this means about the system in general. So to do this, I actually developed a method which was most similar to logistic regression. So logistic regression is a machine learning model where you can take the data set that you have and split it into events and non-events and optimize to find events. And so it's easiest to sort of look at it like this, where on the lower axis, on the lower bound of this axis, you'd have the non-events. And then you're trying to predict the events up here based off of some data set that you have previously identified. So the really important things when I was doing this, though, was that I needed this decision threshold and this curve to be based on something that was defined in physics, such that I could then back out what it meant if you have more events here than somewhere else. I also wanted this to be flexible for different types of data challenges, for example, the spacecraft moving around in space and time, or, for example, missing data, which is a common problem in all planetary data sets. And so where this went is that it really allowed us to build something that was based off a pretty simple machine learning model to create something that was standardized as well as physics-based. And so that's what this plot is showing here. So these gray envelopes are the entire data set from Cassini, and then the little pink dots are all the interchange events. And so what S is doing, this derived quantity that I've created, is it's splitting up the pink dots from the background. And so the pink dots don't overlay the average background, and that's really important because we want them to be different. So moving on from that, because we were able to do this, we then could compare our work to previous studies to understand sort of where this method becomes more useful. We are able to really understand interchange, or these different interchanging plasma populations within the context of larger dynamics. And then we were able to estimate really what energy are these events bringing into the system. And sort of as a big picture idea, it really allowed us to move from this very sort of or rough sketch of what could be happening to a more dynamic picture. And I like to have a bit of a disclaimer on this picture. This is not a real picture. This is an illustration of the Saturn system and what we think might be happening based off the findings that we've found. So to drill in a bit further, because I think a lot of people on the phone call are interested in data, one of the things that we found in our first work is that really an unforeseen benefit of doing something like this is it allowed us to automate as well as standardize how we were defining events. So one of the problems in the field that we were having was that we would all disagree on what we would define an interchange event to be. And most previous surveys had done events by hand or by eye. And so their definition of what an event was pretty variable, dependent between surveys as well as just in their papers themselves. And so that's what this figure is showing. On the outside are all the different surveys that had previously detected interchange. And the purple is the current work, our work. And then between these surveys, these bands are showing how many events are shared between, for example, the Kennelly list and ours. And one of the things that is really striking, sort of on first pass about this figure, is that a lot of the lists don't agree on what an interchange event is. So out of hundreds and hundreds of events over the course of Cassini, we only found 26 that we all agreed on that were interchange. And so creating sort of standardized methods is really useful for this type of work to start to unify our field around different definitions. And so I just wanted to highlight it. So moving on from this into some more sort of high level, what does this mean for machine learning in our field? Really this S parameter that we were defining and trying to use, this was really based off of talking with experts in the field and defining something that represents the space physics of the system. And it's a pretty simple feature in general. It's just one number that runs through the data set. And sort of showing you what this looks like, that simple feature, we ended up comparing it to more complex models in machine learning, as well as models that had access to richer data sets. And so that's what these two are showing. We have a simple model, so logistic regression, which is what we built off in the first place, and then a more complex model, random forest. And then we ran different iterations of these two for different data sets. So for example, the original machine learning model is in purple. And then we have different subsets of the data set on the same model. So what these plots are sort of accuracy plots for different classification machine learning models. And really what you want out of a plot like this is you want your curve to be the closest to the upper left corner. So looking just at logistic regression right now, the original model, which is a single physics-based feature, was able to outperform other models because it's closer to the upper left corner that had access to a much larger data set. So for example, the blue curve has about 5 to 7 more features more than the purple curve. Then moving to a more complex model, you actually see that you have the same performance as this simple single feature model, but you have to include a lot more data to get to the same performance. And so sort of putting this together, by including what we knew about the system into this S parameter, we were able to create a much more simple model that was more useful to our field in space physics, and that allowed us to really create something that was able to handle some of these planetary data challenges more effectively than, say, a more complex model with more data access. So putting this sort of into perspective, there is this idea in machine learning, usually where if as you build your model, this idea is that as you increase the performance, it becomes more and more difficult to understand what's going on, or your explanations for your system are becoming less and less effective. And I'd actually like to say that this sort of idea is false. And if you care more about this, I didn't think that we'd want to go. I hear someone speaking, but they could not be speaking to me. I don't think they're speaking to me. So you can read the Rudin paper that goes more into this, which is where this figure is from.
So we're not going.
Why would I pay $200 to sleep on an air mattress?
Excuse me, someone is unmuted.
No.
I don't see anyone else who's unmuted.
I don't see anyone.
Okay. Do you know who else going?
It's like a ghost person. I don't hear them anymore, so I'm gonna keep going. So if you care about sort of what this looks like in machine learning, I recommend the Rudin paper. But our model in particular did not follow this curve. And it said that more simple models and highly performing models actually had greater effective explainability for our field in space physics because they were grounded in a physical data set. So the sort of next thing that I just want to mention, and I won't go that deep into it, you can ask me about it if you're curious, is that for optimizing these different types of space physics models, we found that for our interests, the preset sort of options for a machine learning model, you can usually weight by uneven classes or not. And both of those choices were not quite right for us. And we found that actually using something which is more commonly used in space physics as well as weather prediction was really where we wanted to say, what is the cutoff between what an event is or not? And so you can sort of see it as this middle option between class-weighted and non-class-weighted. So anyone who is doing sort of classification type of models in space physics, I recommend that they look into optimizing by a different parameter, depending on what they're trying to do with their data set afterwards. So in conclusion, really looking forward, incorporating different types of domain knowledge, for example, space physics or planetary knowledge, allows you to create models which are more useful for your domain community or your home field. And this creates a much easier time so that you can answer fundamental science questions. But I will say that it did take quite a bit of time to create a model that was really based off of the physics of the problem. But I think our community in Planetary can really share lessons and learn from other fields. So for example, earth science faces similar data challenges and they have similar interpretability needs, particularly in climate science. And so we can learn from that field about how we can go forward. And as part of learning from that field, I just wanted to highlight a recommendation that we just put into a white paper to the decadal survey, saying that it would be very beneficial for NASA and other agencies to work in collaboration with the NSF EarthCube program. So if you're familiar with EarthCube, it's basically a data-rich, transformative program which is trying to create what I consider a data science track in earth science. And something like this that focuses on space, so for example, one of my co-authors actually called it Space Cube, would be incredibly influential for our field and fund the type of work that we need. So sort of last things, thank you to the organizers for arranging this weekly lunch series. Thank you, Chase. And I want to thank all the other co-authors on this white paper that really worked together to come up with that recommendation. And then we do have we're starting a monthly series. If you care more specifically about machine learning, you can go to ML4 Planetary Space Physics, psp.github.io, and sign up, and you can get little monthly invitations to seminars. So, and we do not conflict with this seminar on purpose.